I want to start with a quite mysteriously looking example in the beginning. 1228. So I have two examples, but I will not do the second one in detail, but you will find everything in the lecture notes. So first of all, let h be an arbitrary continuous function from R to R. And now we define the function that we want to derive. Capital F from R2 to R is defined by capital F of xy is the integral from 0 to the sine of x plus y of h of t dt. Okay, this looks weird in the beginning. So what does this have to do with the chain rule? We can write this as a composition of maps we know to be differentiable. Namely, then f is given as the composition of maps G and small f, where f is the map which goes from R2 to R, which just has f of xy is the sine of x plus y, and G is the map going from R to R, where g of x is just the integral from 0 to x h of t dt. Okay, if I would have an audience, I would now ask, what do we know about this map G? This popped up in the fundamental theorem of calculus, because we have seen that such a map, if the integrand here is continuous, which we have assumed, this is always differentiable, and the G is differentiable with, this is what we've seen, this is the main part of the fundamental theorem of calculus. The derivative of G is H. Okay, this magical connection between integrals and derivatives. And so F, there we obviously see that this is continuously partially differentiable, so all the derivatives exist and are continuous, so F is differentiable. Let me not elaborate on this further. So by the chain rule, F, so capital F is differentiable with the following property: df in a point x, y of a vector v1, v2. This is now the same as dg in the point f of x, y, composed with, applied to df in the point x, y on the vector v1, v2. Okay, so this is, to be very explicit, this is dg in sine of x plus y, just by definition of f, of df x, y of v1, v2. So g is only a one-dimensional function, and we've seen that the differential of a one-dimensional function as a linear map is just multiplication with the derivative. So this is the same as g prime in sine of x plus y times the differential of f in x, y of v1, v2. So here we've seen that this is just h, so here's just h of the sine of x plus y. And now here the differential, we again use the formula by partial derivatives. This is d1f xy times v1 plus d2f of xy times v2. And the partial derivatives are here easy to compute. So here it's h of the sine of x plus y. And so the first partial derivative of, here we've got the function sine of x plus y. So the interior derivative here of this inner function x plus y is just 1, so there's nothing happening there, but the exterior derivative is the cosine. So we have cosine of x plus y v1 plus, and for y it's the same thing. If we derive this by y, this x doesn't matter, so there's no, the interior derivative is just 1. So again we get cosine x plus y times v2 times v2, and just simplify this as h of the sine x of x plus y, x plus y times the cosine of x plus y times v1 plus v2. So this is the differential. This is df in x, y applied to v1, v2. Okay, first application of the chain rule. Now one more explicit example, and just I'll leave out most of the details. So again, you find the full computation in the lecture notes. So let H be the composition of maps G and F, which I will define in a second, going from R2 to R, where, so I have to check, F goes from R2 to R3. F of x, y is e to the x sine y, e to the x cosine y, and simply e to the x in the third component. So from R2 to R3, and G goes from R3 to R. This is just a polynomial, so this time we have three variables, and I will now call them x, y, z. This is usually simpler to memorize than x1, x2, x3, but you can do this any way you want. So this is then 3x squared minus 2xy plus 4z squared, some polynomial in degree 2. Okay, now what do we need to do? So one can compute that all partial derivatives exist and are continuous. This is quite obvious because these maps in the components are obviously differentiable. All partial derivatives exist and are continuous. So f and g are differentiable. So by the chain rule, H is differentiable. So the differential is then dH in the point x, y. This must now be dg in the point f of y, f of x, y, and we will just enter the definition already. This is e to the x sine y, e to the x cosine y, e to the x. This looks ugly, but this is how it is. This is the point in which we are studying this, composed with df in x, y. Okay, so to compute this, you have to compute the partial derivatives, of course, and here I will skip the details. So you compute that df of x, y of a vector v1, v2. So this is, of course, d1f in x, y, v1 plus d2f in x, y, v2. So this time, these are three-dimensional vectors, of course. These are elements of R3, so it's just component-wise multiplication. And if you just do the computation of these two partial derivatives, which is not that hard, and you could maybe pause this video and just do this simple computation, and then put everything together in one vector, you get that. So here I skip the details, and this gives e to the x of times sine of y times v1 plus cosine of y times, I should have started on the next blackboard, sorry. Let me, need more space. Sorry about that. So this, oh no, I've got space here. Okay, sorry, this put in one vector. So the first component is e to the x of sine y times v1 plus cosine of y times v2. E to the x of cosine of y times v1 minus the sine of y times v2. And in the third component, we have e to the x v1. This looks a bit different because there's no sine or cosine in the third component of f. So this is the vector we get from here. So the differential of f is a map from R2 to R3. So the differential takes a vector in R2 and gives a vector in R3. And this holds for arbitrary xy in V2 and V1, V2 in R2. This then means that if we put in this into the differential of g, so we have, so the result that we want to have is dh of, in the point xy of v1, v2, and this is now just the differential dg in this point f of xy, so e to the x sine y, e to the x cos y, e to the x, applied to this vector. So, let me squeeze it in here, e to the x times sine y v1 plus cosine y v2, e to the x of cosine y times v1 minus sine y v2. Sorry for squeezing, but there's the full vector, so e to the x v1. And now there's just some vector, which looks messy, I agree, but this vector inserted into the differential. And just as we did before, we can use this formula by partial derivatives and compute the differential by this. Namely, we get the first partial derivative, d1g, in the point we're studying, which is this one. So d1g in the point e to the x sine y, e to the x cos y, ex, times the first component of the vector that we put in, so times this, e to the x sine y times v1 plus cosine y times v2, plus the second partial derivative of g, again at the same point, e to the x sine y, e to the x cos y, e to the x, times the second component of this ugly vector. Just put this inside, e to the x the cosine of y times v1 and minus sine y times v2, plus finally the third partial derivative of g in the point e to the x sine y, e to the x cos y, e to the x, times the third component of the vector. This is a bit simpler. This is just e to the x v1. Okay. This is something we have to compute, and this is the point where I'll stop. Because the partial derivatives here, this is just a polynomial, this is not that hard to compute. I mean, the partial derivative of this, come on, that's not that difficult. And then you just have to insert this for the variables and then do some arithmetics here and just combine the terms in the original way, but there's no new difficulties. You just have to apply the same scheme. The vector looks ugly, I agree, and the maps don't look that nice, but you just have to apply always the same scheme by taking the partial derivatives, multiplying with the components, and so on and so on. Let me just give you the final result. So in the end, we get e to the 2x times 6 sine squared of y minus 4 sine y cos y plus 8 times v1. So I'm just writing this as a linear combination of v1 and v2, so we can see the linearity there. Plus e to the 2x times 6 sine y cos y minus 2 cos squared y plus 2 sine squared y times v2. And now if you're a real mathematician in your heart, you can't leave this as it is because there's a lot of trigonometric identities that we can use there. We have seen some formulas like angle sum formulas and so on for the sine and the cosine. And if you play around with these formulas a little bit more, then you end up at a slightly simpler equation, and this is just e to the 2x. So 3 cosine of 2y minus 2 sine of 2y plus 11 v1 plus and this e to the 2x is just in front of everything, plus 3 sine of 2y plus minus 2 cosine of 2y times v2, and then close the big brackets. Sorry for squeezing again. As I said, you find the details in there. So this is just trigonometry, but until here it's just really the standard scheme that we always use here. So you can see it gets a bit complicated. But it's always the same scheme, even if there's a lot of variables, but you always have to do the same things and just practice. That's basically the best advice I can give you on that. Okay, a little more about differentiation and the rules after erasing. After we have seen these examples for the chain rule, I want to establish one particular case as a corollary, because this is some case that pops up occasionally all the time and which connects nicely to mathematics 1. Namely, we consider the following situation as corollary 1229. So, assume we have an interval I. Assume we have an open subset U of Rn. Assume we have a curve which maps into U, so a curve in Rn whose image lies in U. A curve in Rn. Please recall, a curve is just a continuous map so far. And assume we have a map which is defined on U, namely f from U and now mapping into R again. And assume we have a point t0 in the interval I. Now, if gamma is differentiable in t0, f is differentiable in gamma of t0, so on the image point, then by the chain rule, the composition of these two, which is f composed with gamma, and now it becomes interesting because this is now a map which goes from I to R. So this is just a differentiable function from an interval to R, so this is a notion we've already seen in the last semester. So this is differentiable in t0 with the following. So we have now introduced differentials as maps. But of course, getting back to the previous semester, we have seen differentials at the point of such maps from I to R as numbers. So the derivative there is a number. So what is then the number there? What follows from the chain rule if we take f composed with gamma and take the derivative in t0? So by construction, a real number. This has an explicit formula because this is simply, so by construction, df in the point gamma of t0 applied to gamma prime of t0. And this is now a vector in Rn. This is the derivatives of curves are defined component-wise. So we have such a vector there. And if we just compute this in detail, this means we get the sum from I to n, and this is now the standard formula for derivatives, dif in the point gamma of t0 times gamma I prime of t0, and now where the gamma I are the components of gamma, so gamma is gamma 1 to gamma n, and gamma I is then going from I to R for all I. So just the components of the curve. So this derivative as a number is given by that number. And since the chain rule is a construction which says something about differentials as linear maps, I just want to make precise how this statement about numbers then follows from that. And this is easy to see now, because we have seen that the derivative has an interesting property. Namely, this is Theorem 4.6 from Mathematics 1. So this is really from last semester. Sorry, just made a little mistake. By this theorem from Mathematics 1, and let me just outline this here in this box which doesn't actually belong to the proof. If we have a function from I to R, which is differentiable in some t0 in the interval, then we have g of t0 plus h is g of t0 plus the derivative of g at t0 times h plus this rubbish function, which has this nice limit property, but this is not relevant, not too important here. The idea is now that we use the similar notion or the analog of this for the definition of the differential as a linear map. So in the one-dimensional case, we see that the differential as a linear map is multiplication with this number here. This is the linear map we are studying. I've mentioned this in the beginning when I talked about differentials as well. So in the one-dimensional case, the differential is really multiplication with that. So in the other way around, so we've seen, let's maybe formulate this. So the differential of f composed g, so the special case of g is f of this composition form here. This means the differential of f composed with g applied to h in R is just f of g, f composed with g with gamma prime in the point t0. This is f composed with g prime in t0 times h. So for all h in R. Now, this is just the thing that I've put in the box up there applied to this particular case. But this then implies, so if we just want to compute this number, we just have to insert h equal to 1 and get. So this means f composed with gamma prime in T0 is d of f composed with gamma in T0, applied to 1, so as an element of R1, which is put in here. And now we can use the chain rule, because this, by the chain rule, this is the same as the composition of the two respective differentials, and this means we have df in the point gamma of T0 applied to, and then d gamma in T0 applied to 1. Okay, this looks like that. And if we take a look at the definition of the derivative of a curve, this is just as, if we take it as differential, this is again just component-wise multiplication with the corresponding component derivative. So this applied to 1 is simply the derivative vector, so the velocity vector of the curve. So this is the same as df in gamma of T0 applied to gamma prime in T0. And this last step, so this is then just the corollary that we use for computation of differentials in terms of partial derivatives. That was corollary 1217. So corollary 1217, this shows that this final formula holds. The sum from 1 equals 1 to m, dif in gamma of T0 times gamma I prime in T0, and this concludes the proof. Okay, so this is a special case, so we have actually a real function but can compute its derivative in a way which looks unnecessarily complicated, but there are some situations where this really comes in handy, because this compositions of this kind are really often studied. For example, if gamma is describing some curve of, let's say, the trajectory of some particle in a physical system, and you want to measure something, so some quantity, say the energy or whatever, or you have some function which measures a physical thing. So this would be kind of measuring kind of how this function f, let's say the energy, would behave if we travel along the curve. So in this setting, you always have these kinds of compositions. So I just want to put this there explicitly. Now, for the next theorem, I need more space because there's a matrix involved. Namely, so we've seen that differentials are by definition linear maps between Rn and Rm. And we've seen in the linear algebra part before that linear maps between these vector spaces Rn and Rm are always described by matrices. So I have discussed the notion of linear maps induced by matrices, so also differentials must be induced by matrices. Now, the question is, what do these matrices look like? And this I will combine a mixture of theorem and definition, 1230. So we again have m and n in n, u in Rn open, a point in u, and a map from U to Rm is differentiable in this particular point A. Then the linear map, which is the differential of f in A, this is by construction a linear map from Rn to Rm. So this is induced by a matrix, and this is induced by the following matrix. This is now the theorem part of this hybrid of theorem and definition, is induced by the matrix, which I will call J with index f in the point A. And now, okay, this would be a nice question for the audience, and I hope that everyone will be able to answer this. So what dimensions does the matrix need to have? It goes the map goes from Rn to Rm, so we need an m by n matrix, m rows and columns. And the matrix takes a particular form because we have seen already that the partial derivatives play a crucial role there, and it turns out that this matrix just contains the partial derivatives in an organized way. Namely, we start with d1 f1a. This is, I can already add this, where f is again just f1 to fm. These are the component functions. So fi goes from u to r for all I in 1 to m. Okay, so the rows of the matrix now index the functions here. So that we're going from 1 to m. So if we go downward here, we have d1 f2 of a until we get to d1 fm of a. This is now a bit misleading because usually when we have the indices of a matrix of the form aij, we think that the first index is for the rows, the second is for the columns, and here it's just the other way around. That's just how it is. So this is a bit, easy to make that mistake to mix these two up. So here you have to do it the other way around than you would usually do it in a matrix. This is the only hard thing about this to memorize. And if we change columns, we just change the derivative, the component by which we derive partially. So instead of the first partial derivative, the next one takes the second partial derivatives, d2 f1 of a, then d2 f2 of a, and so on to d2 fm of a. I need some more space, so let's remove these unnecessary bars. And we do this, of course, until we arrive at dn. So this is a subset of Rn on which the function lives. So we have n variables here. So we go to n partial derivatives. Okay, so here it's dn f1 in A, then we have dn f2 in A, and finally we have dn fm in A. So this is induced by that matrix. So just as a reminder, this means dfa of the vector v is just matrix multiplication by jfa. So jfa times v for all v in Rn. Okay, this is the theorem part, and now the definition part. This matrix J is named after its inventor, is called the Jacobi Matrix. Actually, it's a German mathematician who was called Jacobi. So Jacobi is, anyway, the English version of that. The Jacobi matrix of f in A. Okay, this is what we're handling. So this is the Jacobi matrix. I'm pretty sure you've already seen this matrix somewhere in your theoretical physics classes. And maybe already done some computations with it. So I hope this is not too complicated for you. Okay, let's take a look at the proof. So what do we know from linear algebra? It's basically we need to apply linear algebra. So there we've seen every linear map was induced by a matrix, and we also could say what the matrix contains. Namely, by remark, so much earlier in this semester, remark 8.6. DFA in this particular case, so this particular matrix linear map from Rn to Rm is induced by the matrix. First of all, it's just some matrix A, which is an m by n matrix. This is what we already know from linear algebra, m by n with R, with real entries. Sorry about that. Yeah, put this right there. So we have some real matrix, and we have seen that so how is this matrix? What does it look like? This would also be a nice question for the audience. So some of you, at least those of you who are preparing for the exam, should know this. What are are the properties of this matrix? How do I obtain this? And the idea was the following: the columns of the matrix, so whose column vectors are, and then again up to just identifying points in Rm with columns, but those are simply given by df A applied to E1 and so on, and just by the images of the canonical basis vectors. This is what we've seen. So df A E2 and so on to df A EM, En, yep, En. But we have seen, this is again by this corollary 12, what was it? It's still somewhere here, 1217, yeah, by this representation in terms of partial derivatives. So dfa of the ith canonical basis vector is nothing but the ith partial derivative in A. And now we just need to take a look at what's in there. So we see that the partial derivatives are defined component-wise. If we do, this is defined by derivatives of curves. They are defined component-wise, so partial derivatives are defined component-wise. Meaning, if we take the component functions of f and derive them by I, these then form the derivative of the big one. So this is just di of the first component, and this was named f1 down there. So di f1 of A, and so on until we get to di fm of A. And this is all we need. This is just by what we know about the differentials. This is linear algebra. And so if we just take these vectors here and put them into the columns, we get precisely this matrix here. This is just, so consider as vectors now. This first column is the first partial derivative of f. This is the second partial derivative of f, and so on. And here's the nth partial derivative of f. So this already shows the claim. So for all I, of course, and this shows the claim. So we can really characterize a linear map by a matrix. This will come in very handy later on, because what we will also take a look at are about some properties of this matrix, namely at some point when we study the inverse function theorem, we will be interested in when a map is when a differential is invertible. Invertible is a linear map, and we've seen that a linear map is of this form is invertible, so bijective, so it's an isomorphism. This is what I was saying, sorry, the linear map is an isomorphism if and only if the corresponding matrix which induces this map is invertible as a matrix. And so for the invertibility, we can study this matrix, and we have also seen in the invertibility, a matrix is invertible if and only if its determinant is non-zero. So we have this gives us a computational strategy to show if the differential of a map at a point is an isomorphism. So write down this matrix full of partial derivatives, compute its, so this is just some matrix full of numbers, compute its determinant, and check if it's zero or not, and then we'll know. So this is, here I should have said, this of course only makes sense if it's an isomorphism, and this is what we've already seen, if the dimensions are the same. So if the Jacobi matrix is indeed a quadratic matrix. So this we will see if m equals n, then we have a quadratic matrix here, we can talk about the determinant and so on, and we will relate this to the invertibility, so the isomorphism property of the differential, and we will see that this tells us something about the map itself, if the map itself is bijective or not. At least locally. This is what we will see later in 1 or 2 weeks. There's not much time left anymore, but anyway, this is what we will see towards the end. And so this is at some point where we can then also use the Jacobi matrix, and of course it gives us a lot of information that we need about the map. Okay, let me erase, and then we'll do the rest of the section. Let us discuss one last corollary about these Jacobi matrices. Namely, we can say something about their products. And so this is also useful for computing derivatives of compositions, namely in the following way, that L, M, N in N, and we have U in Rn, which is open, and we have V in Rm, which is open. And we have F going from U to V, G going from V to R to the L, and a point A in U such that F is differentiable in A. And guess what? G is differentiable in F of A. Okay, so much for that. So we know that from the chain rule that the derivative of the composition is the composition of the not derivative, differential. The differential of the composition is the composition of the differentials correspondingly. But this means for the Jacobi matrices, we have seen that the composition of linear maps for the induced matrix, this is the same as matrix multiplication. This is basically how we defined matrix multiplication. So then the Jacobi matrix of G composed with F in the point A is the product of the two individual Jacobi matrix, namely the Jacobi matrix of G in the point F of A times the Jacobi matrix of F in the point A. So this product of the two matrices, so this matrix multiplication, this is just purely algebra. So if we know the partial derivatives of F and of G in this point, we can compute the partial derivatives of the composition. Namely, these are all the entries of these matrices. And this basically means, so this is matrix multiplication, of course, or just a sanity check. F is mapping from a subset from Rn to a subset of Rm. So this matrix must have M rows and N columns, so an M by N matrix. G is mapping from Rm to Rl, or a subset of Rm to Rl. So the matrix must be an L by M matrix. So we have an L by M matrix and an M by N matrix, which means the product is well defined and gives us an L by N matrix. So this is an ML by NR. Okay, so for the partial derivatives, we just need to give names to the component functions of f and g, namely with f to be f1 to fm, g must be then g1 to gl. And now let's just give names to the component functions of g composed with f, and for simplicity I will name them h1 to hl. Okay, I will not define these are all maps mapping to R, of course. We derive the following, and this is just definition of matrix multiplication. Namely, we get that the derivative dj of hi of A, this would be the ij component of this Jacobi matrix here. This must now be the ij entry of this product, and this is by definition of the Jacobi matrices in there, the sum from k equals 1 to m of dj fk in A times dk and now gi in A. So this holds for all I between 1 and L and all j between 1 and n. Okay, and this just follows if we do the computation and write down explicitly. I will not write down the proof there because this just follows from this linear algebra fact that the composition is induced by the matrix product. Okay, so this really is actually a useful formula because this might look a bit ugly, but this is how you can really compute partial derivatives quite efficiently. So just if you have some arbitrary composition that looks wild, you can just apply this formula if you need particular partial derivatives and you're done. Okay. This is so much for this, enough for this section. So this is what we learned, how we can compute derivatives basically. We have seen many rules. Not everyone is as complicated as this, but we have seen that we have the product rule, chain rule, and so on. So we can really compute derivatives in this way. In this next section, we will then study further properties of differentiable maps, namely some generalizations of results from Math 1, namely, for example, a mean value theorem in several dimensions and some other results that have generalizations. And we will basically collect them in one big, not that big, but in one section then. See you in the next section.